First, we'll discuss shell and tube heat exchangers. Then we'll demonstrate testing boilers and large condenser units. There are three potential problem areas to explore with shell and tube heat exchangers: fittings, headers, and tubes. The leak detection methods we will use include general scanning mode procedures using the contact probe, pressure, vacuum, and tone methods. In an online environment with equipment under pressure or in a vacuum condition, a leak will move from the high pressure side to the low pressure side, generating a turbulent flow with strong ultrasonic components. These sounds are detected with the ultraprobe using the scanning or contact mode. To locate a leak in fittings or headers, use the scanning mode. With the ultraprobe scanning module in the fixed band position and set at log, scan a general obvious area. Adjust the sensitivity on the ultraprobe to focus in on the loudest point, moving from gross to fine sounds, or closer and closer to the leak site. You may need to use the rubber probe. Confirm the leak by moving back and forth across the site. Check all the fittings as well as the headers. The scanning method is explained in full detail in UE Systems leak detection training videotape. To check for potential tube leakage, the contact probe is used to listen through the shell wall. Create 4 equal test zones. Touch the shell in each zone on both sides, listening for normal turbulent flow in the heat exchanger. A leak will be noted by a change in the turbulence. This will normally make a popping or crackling sound. If you're unsure about what you're hearing, compare the sounds with those of other heat exchangers in a similar area with similar load factors. If there is insulation around the heat exchanger, make plug holes and test each time at these sites. Never use the contact probe to create a hole. The pressure will damage the transducer. Check 4 test locations on one side, then 4 locations on the other side. This method is effective for ongoing monitoring of gross tube leakage. Small leaks in peripheral tubes or gross leakage in central tubes can be detected. In an offline environment, 3 methods for testing tubes are used: the pressure, vacuum, and tone methods. The pressure method is conducted by first sealing up outlets to prevent the gas from escaping and connecting house air to the inlet. The system is then pressurized. Test the system as previously demonstrated. Listen for the characteristic rushing sound of a leak with the ultraprobe scanning module. Once the general area of the leak has been found, insert the rubber focusing probe and compare the sounds to neighboring tubes. A leaking tube will produce a louder sound. Test both ends of the heat exchanger. There are certain systems which may not work with pressure. In this case, create a vacuum with a vacuum pump and use the same scanning procedure we've just described. When it may be considered too difficult or time-consuming to use the pressure or vacuum methods, the tone method should be used. Blow all the tubes free of debris and liquid, which will block the sound. UE Systems WTG-2SP warble pipe tone generators are used. Use as many tone generators as may be necessary in order to achieve as uniform an ultrasound field as possible around the tube bundle. As an example, place one in the inlet port and one in the outlet port. Proceed as with the other leak detection methods, scanning for the sonic penetration of the warbling tone. In some exchangers, if sound does not travel to the far end, both ends should be tested. The tone may also be blocked by baffles or support sheets. If more sound is needed, you may use more tone generators with existing fittings in the central area of the heat exchanger. Or you may create additional fittings for testing purposes if your company's policies permit. In certain situations, it may not be possible to use the tone method. In these instances, use the pressure method. In peripheral areas, create zones for comparison testing of tubes with similar intensity readings and sound quality. Since tone generators are on top of peripheral tubes, they will be vibrated during testing of areas near the generators. For an accurate test, test one zone at a time. Reduce the ultraprobe sensitivity to read about 50 on the meter and scan for variances between tubes. Another variation may be to retain maximum sensitivity and reduce the warble tone generator's amplitude while scanning for these differences. As we move away from these areas, sound intensities will change, producing new zones. When you see a change in intensity levels and recognize there is a new area, readjust the sensitivity to read 50 on the meter again and continue testing until you enter another zone. For central areas, bring the ultraprobe sensitivity back up to normal. You may also increase the amplitude of the tone generator as the distance away from the vibration area increases. Use this method to check the integrity of the tube roll. Grossly thin spots along the tube will vibrate and therefore may also be recognized. Next, we'll take a look at tests for boilers and condensers. This program is concerned with boilers which have tubes or tube sheets which can be accessed for pressurizing and scanning. We will discuss testing boiler casings, blowdown valves, tubes, and tube sheets. Boiler casings are tested using the ultraprobe scanning module in the fixed band. Scan the casing itself at a set distance. Listen. Sometimes you may need to use the rubber probe. Adjust for background noise which may interfere. Blowdown valves are checked by using the contact probe on the downstream side. There should be no flow. When testing tubes with the system pressurized, use the scanning module. If there is steam in the tubes, it will be necessary to scan at a distance. Note the area with the loudest sounds. Adjust the sensitivity to pinpoint the leaking tube. Next, we'll discuss testing condensers. Large condensers are usually tested for air in leakage. This introduces impurities into the system and can advance corrosion. We will discuss testing techniques for fittings around the condenser and condenser tube integrity. And we will demonstrate how to handle steam impingement. To test fittings such as valves, piping, and flanges, scan for a rushing sound or white noise. Use the scanning mode of the ultraprobe as shown earlier. Adjust the sensitivity to move from gross to fine sounds, and move back and forth to confirm the leak site. Ultrasound is more frequently the method of choice for testing the integrity of condenser tubes while the condenser is at partial load. Other non-technical methods, such as using foam, smoke, or plastic wrap, are far less sensitive, and the more sensitive helium method is time-consuming. Ultrasound is fast and accurate. To locate a leak site with the ultraprobe, conduct a quick scan, listening for an obvious problem area. If a sound pops out from the background noise, you may be able to get closer and pinpoint the leak site this easily. If a quick scan is inconclusive, divide the condenser tubes into testing zones. Start scanning peripheral tube zones where sounds are loudest. Set the ultraprobe to log and use it in the fixed band position. With the rubber probe, scan a sample tube and adjust the sensitivity to read 50 on the meter. Scan for the loudest deflection in the test zone. To intensify the sound of air and leakage on the inlet side, seal off the outlet tube with plastic wrap. When the loudest area is found, scan around in a star pattern to ensure it is louder and of a different sound quality than the surrounding areas. Mark the loud tubes with cork plugs. A natural progression from one zone to another will be noted by a change in the meter reading. Readjust the sensitivity and repeat this process in each of the test zones, moving to central tubes when peripheral zones are completed. At the end of the test, you will see a visual pattern of corks which may help you determine areas of future investigation for eddy current testing. Next, we will discuss how to handle the problem of steam impingement. As steam rushes across condenser tubes, it generates a noise with ultrasonic components similar to those of a leak. This sometimes confusing sound is called steam impingement. To differentiate between steam impingement and air-in leakage, use the vacuum leak confirmation module in place of the regular scanning module. Seal off the end of the suspected tube, isolating it from the rest of the tube sheet. Then listen and observe the meter. At this point, we have effectively moved the vacuum flow from the tube to the hole by the vacuum leak confirmation module. Depress the plunger to seal the small hole near the scanning transducers. If there is a vacuum leak, the meter will drop. In the case of steam impingement, the meter stays the same. One last technique for locating a leak site should be mentioned. It is highly effective, but can only be conducted during an outage. Use Hogger pumps to generate a large vacuum on the steam side. Then scan inside the inlet and outlet tube sheets for leak sounds. The speed, accuracy, and ease of the ultraprobe will help you locate costly leaks, making it well worth your efforts in the initial startup of your testing program. You will soon see why the ultraprobe ultrasound method is rapidly becoming the method of choice for leak detection.